Good afternoon, ladies and gentlemen. My name is Benjamin Kerr, and here is Christine Kim, Rowena Kanj, Surila Kadali, and Amy Zhang. We are the biomechanics team here at GSIT, and today we're going to talk about the effect of excessive backpack loads on the human posterior trunk muscle. So what exactly are we going to be talking about? First, we'll start off with the background of this project. We'll talk about what's important and talk about the most vital elements of this research. Next, we're going to delve into the actual research. We'll talk about our methods and what we actually found out. Finally, we'll be going into the statistical background of this research. So why is this a problem? In 2007, there were around 23,000 backpack-related injuries in the United States. Out of every 5 students surveyed, 3 of them would report that they had pain related to their backpack. In addition, these same students also reported that they were carrying over 15% of their body weight in their backpack. Why is this a problem? Because over the past decade, each year, around 15% of students have missed school because of pain related to their backpack. This is a significant issue as it creates a huge loss in productivity and time.
Throughout our project, we explored different types of back muscles that were most affected by heavy loads. Pictured here are the trapezius and the deltoid muscles. The trapezius muscle is a largely superficial muscle, meaning that it is located close to the skin. Therefore, it is prone to pinching and injury due to the straps of a heavy backpack. The deltoid muscles are more commonly known as the shoulder muscles. They connect the scapula and collarbone to the humerus. Because this muscle is responsible for raising and twisting the arm, pain is common when the scapula is pushed in an unnatural position. Pictured here are the rhomboid and the serratus anterior muscles. The rhomboid muscles are thin skeletal muscles which enable joint movement. They connect the spine to the scapula. The serratus anterior muscles are superolateral surfaces of the upper ribs next to the side of the chest. It stabilizes the scapula, which connects the humerus to the clavicle. Because this muscle extends up to the arm, excessive use or load will result in pain.
To aid in our research, we use the antibody technology software, which provides us with a full body simulation that also uses inverse dynamics, which would be ground reaction forces, as well as the muscle's upward forces on any load we apply. This software has over 1,000 muscle elements, and it's also very customizable. So we can omit muscles, we can apply external loads to different types of muscles, and then we can chart them to see the results. Through this, we can simulate various scenarios, such as climbing into a car, walking, and carrying heavy loads. To identify our parameters, our control load was 0 pounds, so we did not apply any force to the staging model that was provided by the antibody technology software. We then ran the model and charted the results, and noted the numerical forces on each muscle. We kept the body mass at a constant 75 kilograms, and after this, our experimental groups we decided would be 10 pounds, 20 pound, and 50 pound backpacks. These represent 2 notebooks and a laptop and supplies, and then a 50 pound would be a hiker's backpack that has supplies, food, water, etc. We also tested the effects of applying force to both shoulders, simulating a 2-strap backpack, and applying force to one shoulder, simulating a 1-strap backpack, or a backpack that is only slung on one side. To apply load to the shoulders, we used 3D vector forces, and we altered the code in the software itself. As you can see here, we estimated that the backpack would be pulling back and down on the back at a 15-degree angle. Based on what we wanted our resultant load to be, whether it be 10, 20, or 50 pounds, we then calculated the Y and X direction forces and inputted it into the code and ran the model. After this, we graphed the muscle forces using chart effects and max muscle activity, which are both available through the antibody technology software.
So with the aid of the antibody software, we were able to run a test on several different muscles, including the trapezius muscle, the rhomboid, serratus anterior, and deltoid muscle. To do so, we applied loads of increasing weights, as you can see in this graph here, with no load with the blue bar, 10 pounds with the red bar, 20 pounds with the gray, and 50 pounds with the yellow. It is important to note that a muscle is not one singular entity, but also comprises of what we coined as submuscles. which all serve the same function, but they are still located slightly apart. Because of this, we had to graph, for the trapezius, 9 different submuscles, as they were affected differently as we applied increasing loads. But however, you can see how with no load, the amount of stress on the muscle generally trended at around 5 newtons. However, as we increase the load all the way up to 50 pounds, you can see how some of them went almost up to around 20 newtons. While this may not seem much, you have to note that there are several submuscles, and this can actually combine to be a really large, to create a really large stress on the muscle. In addition, we took a look at the rhomboid muscle. In this case, there was one submuscle that was affected. However, it was affected really greatly. As you can see, it started off at around 0.8 newtons as we had no load on it. However, as we went up and applied 50 pounds, it actually went all the way up to over 8 newtons. This is actually huge because that's an increase of 10 times the normal amount experienced by the muscle. In addition, we decided to take a look at several different other muscles, and we were able to pinpoint 2 that were also affected affected greatly as we applied more and more load to it. In this case, you can see how the serratus anterior experienced in some cases 4 times the normal amount experienced when it had no load. In addition, we also took a look at the deltoid muscle, which experienced similar increases.
After applying forces to the antibody standing model, then the antibody software measured the forces of hundreds of muscles in the human posterior trunk. However, for our analysis, we needed to identify the muscles that underwent severe stress. In order to do so, we plotted our data on a scatter plot and used y-error bars of 1 standard deviation to identify the higher 15% of our data set. This allowed us to identify about 32 muscles and submuscles that underwent severe stress. With these 32 muscles and submuscles, we were able to conduct further statistical analysis. So the following flowchart over here diagrams the statistical process we went for our analysis. We took data for the standing model wearing a 2-strap bag, standing model wearing a 1-strap bag, and then compared the 2 data sets. For each data set for the 2-strap bag and the 1-strap bag, we first compared the data to a control, an antibody standing model without any weight, 0 pounds, and then we also conducted additional tests to see the effect of additional weight. So for the first analysis, we looked at the 2-strap bag data. First, we compared the antibody standing model without any weight, or control, to the antibody standing model wearing a 20-pound 2-strap bag. We chose 20 pounds since that represents approximately 15% of the model's body weight, which was a common value in the literature that we had read. So we used the statistical analysis known as the t-test. The t-test is a statistical hypothesis test to see whether the data supports or does not support a hypothesis. In our case, our alternate hypothesis is that there is a significant difference of muscle forces of the antibody software without a bag and of the antibody model wearing the 20-pound 2-strap bag. So the t-test produces a p-value, and if this p-value is less than our selected alpha, that indicates that the data supports the alternate hypothesis. If the p-value is greater than the alpha, then the data does not support the alternate hypothesis. In our case, we used a p-value of 0.01 it's a standard p-value in most medical studies. So after conducting our t-test with our paired data, it produced a p-value of 8.307 times 10 to the negative 11, which is significantly less than our alpha of 0.01. This confirms that we support our alternate hypothesis, which means that there is a significant difference between the antibody model, the forces of the antibody model with the 2-strap bag, and the forces of the antibody model without any bag. We conducted 3 additional t-tests to see the effect of increased weight with the 10-pound bag, 20-pound bag, and 50-pound bag. All those 3 tests produced p-values less than our alpha, reaffirming that increased weight causes increased stress. The following graph shows the average muscle forces of the antibody model with the 10-pound bag, 20-pound bag, and 15-pound bag. There's an obvious increasing trend, and the statistical test supports that there's a significant difference. So going back to this flow chart, we repeated this entire process for the one-strap data, where we first compared the antibody control, the one without any weight with 0 pounds, to the antibody model with a 20-pound one-strap bag. That also produced a p-value less than our alpha, proving that there was a significant difference. And then we conducted 3 additional t-tests, which all produced p-values less than our alpha, reaffirming that increased weight causes increased stress.
As we collected our data from the muscles affected by the 2-strap backpack and the 1-strap backpack, we are able to produce this graph as a comparison. As you can see, the blue bars represent the 2-strap backpack, and the red represents the 1-strap backpack. In the graph, the red, for the most part, is far greater than the blue bars. This shows our alternate hypothesis, that the 1-strap backpack causes more stress on the muscles. After this, we conducted another t-test for our comparison, and that created a p-value of approximately 1 times 10 to the negative 10. This number is far less than the alpha value of 0.01, and so our data supports our alternate hypothesis. During our time at GSET, our preliminary research was based on the rhomboideus and the trapezius. Through this data, we chose these muscles because they are most directly affected by the backpack straps. We are able to see how there is a much greater strain. However, also in our research, we saw how the serratus anterior and the deltoids had a large percent increase, and because of this, we added it into our research. Overall, these muscles proved our hypothesis correct, how that the increasing weight loads and the varying straps, specifically the 1-strap backpack, had a negative and a large increase of stress on the muscles. During our time with the antibody program, we used the inverse dynamics for a certain moment. Our next idea is to project this into a long-term effect. In doing so, we want to try gait analysis. Gait analysis is having an antibody model and having it actually move. For example, walking. The model will have the force applied to the shoulders and act as a backpack, and as it walks over the time, we can measure the amount of force and see how it affects the stress of the muscles, and also see how the time interval affects the muscles as well. Another idea of ours is to change the model itself. What we used was an average human size of 75 kilograms. Another idea is to use a child model or an adolescent model. We chose these 2 target audiences because they most often wear backpacks for going to school compared to average adults. Because they go to school, backpacks are the most common use to put all of your supplies, which is why we chose these 2 audiences. Another idea was that in our research, we saw that just by applying no load at all, there was also some sort of stress on the muscles. Because of this, we knew that the body mass index, or the BMI, had some sort of effect on the muscles. As a result, we wanted to see the change of body mass indices from underweight, average weight, slightly overweight, and obese, and see how those body masses, coupled with the loads, would affect the stress. Through our time at GSET, we'd like to thank Dr. Nishir A. Langrana for all of his help. He provided with a lot of information that helped progress with our research. Also, he told us to go beyond what literature told us. Before, we only used 2 muscles, the rhomboid and the trapezius, but however, he told us to use our data, and we were able to expand more on our research. We would also like to thank his students, Jacob Jaslov and Maya Saltzman, for their incredible help with the Antibody Technology Program and for their great support for us.
We'd like to thank the sponsors of GSET, including Morgan Stanley, PSE&G, South Jersey Industries, and New Jersey Resources.
We also wouldn't have been able to do this project without the support and guidance of the Governor's School of Residential Teaching Assistants. Specifically, we'd like to thank Justin Yu for his continued guidance and help.
We would also like to thank those who made GSET possible, including Director Eileen Rosen, Assistant Director Jean-Patrick Antoine, Rutgers University, and the State of New Jersey.
And finally, I'd like to thank the GSET Alumni Committee for making these past 4 weeks a great experience, as well as the audience for coming all the way here to listen to us. Are there any questions?
can you tell me about the antibody program? Is basically just a finite element analysis or sort of a fancy truss analysis?
Well, the antibody software incorporates thousands of muscles and joints and everything, and it's very complicated. So we had to go through tutorials as well as work with the code and apply different forces. It was, I think it was created by PhDs to simulate different effects as well as like joint length, muscle, like omitting muscles, muscular dystrophy, such issues as that, and then be able to note the exact like numerical effects of them.
Yeah, it focuses usually on the muscle force, the individual values for specific muscles. So for muscular analyses, it's very useful.
It basically shows how a load distributes itself over the various structural muscles. Right?
Exactly.
Yes, and you can see it in the program. Like once you run the program, specific muscles can they turn different colors and they're more like inflamed, and you can tell that they're stressed.
Gotcha.
Yes, I see a lot of students, including my son, carry a very heavy backpack in just one strap. I guess it's easier to get on and get off. So are you planning to, when you go back to school, are you planning to publish the results in your school newspaper and all of this may be educated?
Maybe. There are a lot of there are a lot of adverse effects of specifically like overpacked backpacks. I know backpacks on one strap, backpacks that hang lower on the back, all of which cause a lot of back problems, which you see mostly in teenagers today, as well as like overcompensation because of just one side, leaning back or arching forward. So it has a lot of dangerous effects that might affect spinal problems in the future. So possibly.
Yeah,
Does the AnyMove software distinguish gender?
No, on the current antibody model software, one limitation for a project is that it has one standard model. You can change the BMI for the software for the model, which in our case, well, it was 75 kilograms, but you can't really. There's no differentiation for gender. Also, there's no differentiation for age, so that was an obstacle. We initially wanted to look at different age groups. However, the muscle ratios don't really change. So as of now, the software is relatively new and such, so it's only one model.
If we had liked to, we really like to test it on adolescents and children. However, because like Srila said, the program is relatively new as well as complicated. If we wanted to scale down the entire body, we have to scale down every muscle as well as every joint and every bone. So it'd be a very long process for someone who's only an expert in the software.
Develop next generation.
Any other questions?
Do you recommend your results to the school system or any other, would you incorporate it with the results of other studies and
Well, we based it off.
to other schools,
Yeah.
Board of Education?
We based it off of a lot of already existing problems with heavy backpacks, as well as the statistics that we had in the beginning. There are tons of statistics online about children who have back pain as young as 11 years old because they're carrying backpacks that are too heavy or are only on one strap or don't have enough padding in the back. So possibly it could be incorporated into other schools, but we'd have to maybe catch them up on it a bit.
Just one other question. There was no indication on your charts that there was a pain threshold. Like in other words, if a muscle was stressed beyond some certain amount or had to bear a certain force, that would be the place where pain would start, right? So do you think you could impose one of those if you took, say, data from whatever the doctors see and so on and so forth?
Yes, that's actually something we were hoping to do in the future. We have found some articles that have like charts. Like we were hoping to look at also bone. They have like the maximum force for breaking bones and such. For they have also for muscle tolerances and such. They have specific ranges. For our initial analysis, this project we didn't incorporate that. That's something definitely we want to incorporate in the future.
It's also very difficult because we actually looked at values such as that, and it's very difficult because it depends solely on the individual most of the time. So it depends how old you are, your weight, your lifestyle, how often you exercise, etc. So a lot of the time muscle thresholds are within a certain percentage, but are not easily defined.